It's important to learn how to be creative. Here's everything you can be taught about how to be creative. While you can't be taught how to be creative, you can still learn it. One way is to examine how an idea is actually created. To avoid learning anything, do an internet search on fast powering algorithm and skip the rest of the video. But if you can do that, so can someone else making half your pay. For some applications, it's necessary to find very high powers of a number. So we might need to find x to the power 34,987 for some value of x. Let's compare the naive algorithm to a divide and conquer approach. We'll assume that each multiplication is one step, for now. The naive algorithm for finding x to the n requires multiplying n factors of x. This requires n minus 1 multiplications. Now let's divide and conquer. Suppose we split the factors into two sets. So we have the first k factors of x, and then the remaining n minus k factors. The first set requires finding k minus 1 multiplications. The second set requires finding n minus k minus 1 multiplications. And we'll need one more multiplication to find their product, for a total of... And this doesn't seem to help it. So a useful strategy is don't worry about solving the problem. Let's consider a different approach. Rather than trying to compute x to the n for a specific x, let's see what we can find easily. We can find x squared with one multiplication. We can find x cubed with one more multiplication using x squared times x. But we can also find x to the fourth with one more multiplication using x squared times x squared. What about x to the fifth? Once we've found x to the fourth, taking two steps, we can find x to the fifth by x to the fourth times x. But note that the method we used to get x to the fourth required us to find x squared. So if we still remember what that is, we can also find x to the sixth with one more multiplication. And finally, we can get x to the seventh by multiplying, which takes us two more multiplications. The key feature to notice is that once we've computed a value, we can store it and use it for later. As long as memory storage isn't an issue, this is a valid strategy for improving an algorithm. We call this dynamic programming. We can assume that memory storage is not important. If we need more memory, we can add more memory. However, we do want to minimize the number of additional values we have to compute. So let's see what powers we can find from the powers we've already computed. Let's consider the product we can find from existing products by using some additional multiplications. From x and x squared, we can get x cubed and x to the fourth using one more product. And now that we have these four products, we can get So what if we computed x, x squared, x to the fourth, and x to the eighth? We could then compute x to the ninth through x to the 16th. Note that the powers we actually need are x squared, which is x squared, x to the fourth, which is x squared squared, x to the eighth, which is x to the fourth squared, and we can continue the pattern. This suggests the fast powering algorithm. To find x to the n, find x squared, x to the fourth, which is x squared squared, x to the eighth, which is x to the fourth squared, and so on. Then select the appropriate powers to multiply to x to the n. So let's find 2 to the 13th. So we'll compute 2 squared, that's 4. 2 to the 4th, that's 2 squared squared, or 16. 2 to the 8th, that's 2 to the 4th squared, that's 256. And if I want 2 to the power 13, that's 2 to the 8th times 2 to the 4th times 2, which will be So let's find big O for the fast powering algorithm. In the worst case scenario, we need to compute and then multiply the k plus 1 terms. Now finding x squared takes one step. That's x times x. Once we have x squared, finding x to the 4th also only takes one step. That's x squared times x squared. And in general, finding the requisite powers only takes one step. So finding these powers takes k steps, and then multiplying them all together takes another k steps. So the fast powering algorithm takes 2k steps, where k is, well, let's figure that out. What's k? Since we want to find x to the n, and we're multiplying factors together, there's no point in finding x to the power 2 to the k if 2 to the k is greater than n. So we don't need to find x to the power 2 to the k if k is greater than log to the base 2 of n. This means we do need to find x to the 2 to the k for all k less than or equal to log to the base 2 of n. So to compute x to the n, we'll need k log to the base 2 of n steps to compute the powers of x, and then log to the base 2 of n additional steps to multiply these together for a total of 2 log to the base 2 of n steps. So fast powering is big O of log to the base 2 of n. Let's see how much more efficient this is. Let's estimate the number of steps required to find 2 to the power 785 using the fast powering algorithm, and then determine the exact number. Since fast powering is big O of log 2 n, we'll need approximately 10 steps where we round up. In fact, we need to compute 9 products, then 4 more products, for a total of 13 steps. Now, suppose we want to implement an encryption algorithm where these very high powers come into play. So we might need to evaluate x to the n, where n itself, that's the exponent, is on the order of 10 to the power 300. Let's compare the naive algorithm to fast powering. The naive algorithm for computing x to the n requires n minus 1 multiplications, so it would require about 10 to the power 300 steps. Fast powering is big O of log to the base 2 of n, so it would require about 997 steps. Note that 997 is approximately 10 to the third, so the naive algorithm would take about this many times longer.